Knowing how to do decimal arithmetic is important even if you're in a class that allows you to use a calculator, because if you understand how the decimal arithmetic works and how to estimate whether or not your answer is reasonable, you're going to know whether or not you're doing a problem correctly, even if you're using technology to assist you. So in this video, we're going to be talking about how do you do things the more old school way and why that old school way is going to allow you to know whether or not your answers are reasonable. So let's start with adding and subtracting. So regardless if you're adding or subtracting, the key thing is you want to make sure those place values are lined up. So if, for example, you're doing 12.5, let's say minus 6.23, you're going to want to make sure that this is lined up where the decimal places are in the exact same place, and therefore your ones are in the same place, your tenths are in the same place, etc. You're also going to want to preview your mind for what you think the answer should be about. So just even paying attention to the whole numbers. I know that 12 minus 6 is 6, so I'm hoping my answer is somewhere in the ballpark of 6. If it's not somewhere in the ballpark of 6, that probably means I did the problem wrong. Now I can actually start to do my subtraction or addition algorithm. For that, you're going to want to start from the right, and if you notice, there's nothing above the 3. That's because there's secretly actually a 0 there, so I'm going to want to go ahead and put in that place value holder. Additionally, if I try to do 0 minus 3, that's not going to work, so I've got to borrow from the place value right next to it. By that, I mean I rewrite my 5 tens as 4 tens, and then I rewrite that 0 as 10 ones. If you notice in terms of, and actually I should have said 4 tenths and 10 100ths, that's actually the place values we're in. If you notice, I haven't actually changed the value of this number, right? This is the number 12 and 5 tenths. 12 and 5 tenths is the same thing as 12 and 4 tenths and 10 100ths. If you don't believe me, do that to the side. 12 plus 4 tenths plus 10 100ths. That should get you exactly the same thing as 12 and a half when you actually simplify it out. But with that aside, let's actually start our algorithm. So you do 10 minus 3, that's going to get you 7. 4 minus 2, that's going to get you 2. You're going to drop down that decimal point. If I try to do 2 minus 6, I can't, and you might be thinking, I don't really need to borrow to do 12 minus 6, but I'm just going to kind of show you anyway. That 1 becomes a 0, that 2 becomes a 12. 12 minus 6 is going to give me 6, and our final answer is 6.27, just like we expected with the 12 minus 6. There's also another example written out here already, but if you want to practice with the same numbers with the addition, you should, again, find that you get the same answer as what is written in this video. But let's try some more interesting examples. So specifically, let's try some examples where we have the subtraction or addition of negatives. So adding and subtracting negative decimals really works the same way as adding and subtracting negative integers. You're just also involving a decimal in there. In particular, if we're taking a look at this first problem here, negative 10 plus 5, I expect to go ahead and be negative 5, because since they're different signs, I'm going to subtract the number and then keep the sign of whichever one is bigger in absolute value. I can always think about it in terms of the money metaphor as well, where that negative 10 plus 5 is the same thing as being $10 in debt, paying back 5, and you're still $5 in debt. So here, if I'm going to be setting up my decimal addition or subtraction, I actually probably want to think about this more in terms of the shortcut way, where I expect this to be the same result as doing 10 minus 5, but then keeping the sign of the bigger number. And that's exactly how I'm going to set it up, but here with all of our decimals. So we have 10.5967 minus 5.9816. With all of the exact place values lined up perfectly. You should, again, in particular, notice that your decimal points are lined up perfectly. And that at the end, I'm going to stick a negative sign on there because I expect that final answer to be negative. Because in reality, I'm actually doing the problem negative 10.5 blah, 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 plus positive 5 point blah, blah, blah. Now I'm ready to continue with my subtraction algorithm. So if I do the 7 minus the 6, that's going to give me a 1. 6 minus the 1, that's going to give me a 5. 9 minus 8 is going to give me a 1. For 5 minus 9, I can't do that yet. So I've got to borrow. And this is actually a good example where I'm going to have to double borrow, because if I'm going to be looking immediately to the left of the 5, I can't borrow from the 0. There's nothing there. So what I'm going to do instead is first I'm going to borrow from this 1, make it a 0, rewrite that as 10 ones. Then I'm going to borrow from those 1s, make that 9 ones, add the 10 tenths over here to make a total of 15 tenths there in that place value. And again, I haven't changed the value of the number that I'm actually subtracting at any point. Now I'm actually going to go ahead and do the subtraction down. I have 15 minus 9, that's going to get me 6. Drop down the decimal point. 9 minus 5 gets us 4. So we end up with negative 4.6151, which from my sanity check should seem reasonable, because I expected something in the ballpark of about negative 5. And negative 4.6151 is close to negative 5. Go ahead and pause this video and see if you can go ahead and do the next one yourself, and then we'll compare answers. So for the next one, this is again where we have mixed signs going on. So we expect if I have a negative plus a positive, that would be the same thing as taking the positive and minusing that number. So in particular, negative 5 plus 8 is the same thing as 8 minus 5. Adding a negative and subtracting a positive are the same thing. So we expect our answer to be somewhere in the ballpark of positive 3. So our final answer will be a positive, and we're going to go ahead and line up these digits very carefully. Now we're ready to subtract straight down. If you don't see anything in a particular place value, you're going to go ahead and put a 0 there. 7 minus 0 gets us 7. 3 minus 1 gets us 2. 8 minus 4 gets us 4. Drop down the decimal point. 8 minus 5 gets us 3. So our final answer is positive 3.427, just like we expected it to be in the ballpark of about 3. I'm also going to go ahead and do one addition example. So if we're doing, for example, let's say 4.73 plus, let's say, 5.9. Again, we're going to light this up like this, where I don't have anything written here in this hundredths place. I'm going to go ahead and put a 0. And now I'm ready to add straight down. So I'm doing 3 plus 0 gives us 3. 7 plus 9, I'm going to write down a 6 and then carry up what's technically the ones place here. So you write down the 6, the rightmost digit, and then you carry up the leftmost digit. I'm going to drop down this decimal point. 1 plus 4 plus 5, that's actually going to get me 10. So I'm going to write down the 0, technically carry the 1 to the next place value. There's nothing written there, so I'm actually going to write that 10 there. And this should about match with our intuition, because if I just did 4 plus 5, that would be about 9. And this is still roughly in the ballpark of 9. So that's how I know that I did the problem correctly. For multiplying decimals, you don't have to actually worry about lining up your decimal points. In fact, I would recommend against it. But what you do need to make sure is at the end you move that decimal point to where you expect it. Now, in terms of checking whether or not the final answer seems reasonable, if you're multiplying and either number is less than 1 in absolute value, you should expect your answer to get smaller in absolute value and get closer to 0. If the numbers that you're multiplying, if both of them are greater than 1, then you should expect your answer to get bigger. And you should expect the answer to be roughly in the ballpark of just multiplying kind of the closest numbers here. So let's actually kind of go through this algorithm here. So if I were to do 2.56, let's say, times 0.2, again, I don't actually care about lining up my decimal places, and if you notice, I'm actually rewriting this just so everybody's sort of flush with the right. Now I'm going to go through my long multiplication algorithm. So I'm going to do 2 times 6, that's going to get us 12, carry the 1. 2 times 5 is going to get us 10, plus 1 is going to get us 11, so write down a 1, carry the 1. 2 times 2 is going to get us 4, plus 1 is going to get us 5. And then technically with kind of the long multiplication algorithm, you would then move on to the next place value. That next place value is a 0, so it would just be a line of zeros that I'd write down here, so it wouldn't actually add anything to the problem. And I've got 1, 2, 3 numbers after the decimal place, so I'm going to move our decimal 3 over, and then there would be a secret 0 out front. So this would be 0.512 as our final answer. And as a sanity check, I am multiplying a number that's about 2.5 by about 1/5, so I am definitely making it smaller than 2.5, and that was the case here. Let's go ahead and do another example. So if, for example, I'm doing 1.2 times 3.4, again, I'm going to do the same thing of it first, ignoring the decimal place, and then I'll worry about him at the end. So if I do the 4 times 2, that gets me 8. 4 times 1 gets me 4. Now it's a non-trivial number in front of the decimal point, so I'm going to go ahead and put down a 0 as a place value holder and move on to the next place value. 3 times 2 gets us 6. 3 times 1 gets us 3. Now we're ready to add straight down. 8 plus 0 is 8. 4 plus 6 is 10, so I'm going to write down the 0, carry the 1. 1 plus 3 is going to get us 4. And then we're going to move our decimal place 2 places over. So we get a final answer of 4.08. And that should be reasonable because I'm multiplying 3.4 by a number that's just a little bit bigger than 1. So I would expect my answer to be somewhere between 3.4 or at most 3.4 doubled would be 6.8. So it should be somewhere between 3.4 and 6.8, closer to the 3.4, and that is indeed what I got here at the end. Go ahead and pause your video and try this next one before we go over it together. So for this next one, you can line these up however, but I usually like to do the number that has fewer digits below, just so that I'll have fewer things I'll be adding up. And then we're going to go ahead and go through our algorithm. So 9 times 4 is going to get us 36, so you write down the 6, carry the 3. 9 times 9 is going to get us 81, plus 3 is going to get us 84. So I'm going to write down the 4, carry the 8. 9 times 2 is going to get us 18, plus 8 is going to get us 26. And then we're going to write down a placeholder value of 0. 5 times 4 is going to get us 20, so write down the 0. And actually, I'm going to move on to using a different color just so that you can see the different type of borrowing. So write down the 0, carry the 2. 5 times 9 is going to get us 45, plus 2 will give us 47, so write down the 7, carry the 4. 5 times 2 gets us 10, plus 4 is going to get us 14. Now you're ready to add straight down. So 6 plus 0 is 6, 4 plus 0 is 4, 6 plus 7 is 13, so write down the 3, carry the 1. 1 plus 2 plus 4 is going to get us 7, and then carry down the 1. We now have 1, 2, 3 numbers after the decimal place, so I'm going to move my decimal place over 3. And our final answer is 17.346. Now for a sanity check here at the end, 5.9 is about 6, 2.94 is about 3, and 6 times 3 gets us 18. So it makes sense that we got a number that was in the ballpark of 18 and specifically a little bit smaller, since 5.9 is a little smaller than 6 and 2.94 is a little bit smaller than 3. So we know we did the problem correctly. Dividing decimals is also extremely helpful. We're specifically going to focus on dividing decimals by whole numbers because those are scenarios that you will run into more in the wild. For dividing decimals by other decimals, there is a variation of this algorithm that we're not going to cover during this video, but it works very similarly. You just have to think a little bit more carefully about where you're going to move the decimal place at the end. But if I'm dividing a decimal by a whole number, let's say something like 5.2 divided by 4, you're really going to treat this as regular long division and keep the decimal place exactly where it is. So in particular here, what would that regular long division look like? Well, you would ask yourself, 4 goes into 5 how many times? It goes in once. Then you would go 1 times 4 is going to be 4. Subtract 5 by 4, you're going to get 1. Carry down the decimal place, carry down the 2, and then repeat. So you'd ask yourself, 4 goes into 12, how many times? 3. 3 times 4 gets us 12. And then lo and behold, I have no more remainder left. So my final answer is 1.3. Oh, and I wrote that in the wrong place. 1.3. So let's actually do this other problem. So if we have 1.17 divided by 3, let's try doing that in a similar fashion. Now, if you want to kind of have, again, that sanity check at the end to know if you're doing it right, for the 5.2 divided by 4, for example, I would know that since 5 is in between 4 and 8, that the answer should be in between 1 and 2, since 4 times 1 gets us 4, and 4 times 2 gets us 8. For 1.17 divided by 3, I know this should be a decimal smaller than 1 because I'm dividing 1.17 by a number bigger than itself. So let's go ahead and go through the algorithm with this. So first I'd ask myself, 3 goes into 1 how many times? 0, so I'm going to write a 0 there. 3 goes into 11 how many times? That would be 3. 3 times 3 gets us 9. If we do that subtraction, 11 minus 9 is going to get us 2. Drop down the 7. 3 goes into 27 9 times, and 3 times 9 is 27, so I have no more remainder. So the final answer would be 0.39. This skill in particular is going to be helpful with word problems, and in particular any word problems that involve money. So if you're ever going to take like a future business class, oftentimes that will involve money, and that money will involve decimals, and it's good to know how to work with those. So if, for example, if you have a pack of 4 batteries costing $3.20, price per battery, as a quick sanity check, I would know that if each battery were $1, that the total cost would be $4. So I know I should get a number that's smaller than 1. And then I can set up my long division. So I'm doing 3.20 divided by 4. 4 goes into 3 no times. 4 goes into 32 8 times. 8 times 4 gets us 32. Do that subtraction. I have no remainder, so it must be 80 cents per battery. It's totally fine to go ahead and tag on an extra 0 there at the end. Even though we normally write the decimal 0.8 just as is, if we're talking about money, we usually like to talk about how many hundredths are there as well. If we have 5.58 and we divide that by 3, we can do it with the same algorithm. For if we have a case of 3 items costing $5.58. As a sanity check, we would want to make sure that we kind of knew that 5.58 is close-ish to 6. And if 3 items cost $6, 6 divided by 3 is 2. That would be $2. So we're expecting a number in the ballpark of 2, but a little bit smaller. So if we go ahead and continue our algorithm, we'd ask ourselves, 3 goes into 5. How many times is that going over? Once. 1 times 3 gets us 3. Do that subtraction. 5 minus 3 is 2. Drop down everybody else. 3 goes into 25 8 times. 8 times 3 is 24. 2 minus 2 is 0. 5 minus 4 is 1. Drop down the 8. 3 goes into 18 6 times. 6 times 3 is 18. We have no more remainder. So they cost $1.86 each, which is about what we would have expected, since that is just a little bit less than $2.